All right, guys. So, in this last section of chapter 6, we're going to talk about one final method that we can use in order to find a Hamilton circuit in order to solve a traveling salesman type of problem. Remember that so far we saw the brute force algorithm, which is nice for finding an optimal route, but also very time consuming, especially for a large number of vertices. So in the last couple of videos, we've talked about nearest neighbor and repetitive nearest neighbor, which are some slightly better ways, definitely quicker ways at finding some alternative routes, which, although they might not be optimal, are at least a little bit cheaper in cost. So in this last section, we're going to talk about what's called the cheapest link algorithm and how it works. So the idea behind this algorithm is that we're going to piece together this tour by picking out different links, in other words, the different edges of our tour based on the cost, which while you might think of as being similar to nearest neighbor, is unique in that we're going to look for the absolute cheapest on the entire graph, even if they don't necessarily connect right away, and even if they don't start necessarily where we want them to. So, to kind of talk you through this, there are two rules which are going to be super important, definitely things that you need to have written down in your section of the notes for cheapest link. The two rules are this. Number one, we are not going to allow a circuit to form until the very end. If we allow a circuit to form before the end of our route, then it's not going to be possible to create a circuit, and it's not going to be ideal for us. So that's the first thing is we're going to always avoid creating circuits until the very end. The second rule is that we're not going to allow three edges to come together at a single vertex. What that basically ends up meaning is that it's once again not going to be ideal and is not going to work. So again, as long as we follow these two rules, we should be able to use this cheapest link algorithm fairly easily. Let's go and take a look at an example of this using that tour of 5 cities. This is the one that we've used for each of the other examples as well, so we should be fairly familiar with this graph. I do believe the slides have a pretty good way of talking you through this, so I am going to not necessarily read word for word, but I'm going to use the slides primarily to kind of explain this to you. So step number one for cheapest link is we're going to find the absolute cheapest path on our entire graph. And the cheapest edge is this one from A to C, which notice they've got that for us right here. And then they've got these arrows indicating our direction of travel from A to C. That may or may not change, we don't know. But we can for sure agree that out of all of the costs on this graph, that 119 is the cheapest. Okay. Our next step is going to be to find our next cheapest link. So after 119, our next cheapest is 120, which connects C to E. So that's going to be the next one that we'll take, and again, we've got that indicated with these arrows. Now, thinking ahead, it might be tempting to look for our next cheapest, which we would normally think of as being 121 from B to C. But that's going to be a problem because we already have two paths coming from this vertex C. If we add 121, that's going to be a third path, and that violates this second rule where we're not going to allow three edges to come together at a single vertex. So that's going to be what this next slide explains, is that for that edge of B to C, we're just going to put an X there to say we cannot use that because of the fact that C already has two edges coming out of it. In fact, we could also do the same with D to C. We could also mark that one off since, once again, C already has two, so we're not going to be able to use it again. In fact, I think what they go ahead and do is they can just go ahead and erase it. So we could even do the same here. We could kind of erase this D to C edge and just pretend like it's not even there. Now, in addition to that, we're also going to start to look for our next cheapest link. And the next cheapest is 133 right here. The problem with that is notice that if we picked that from E to A, we would form a circuit because we would be going from A to C to E back to A. That violates the first rule that we had, which is that we're only going to form a circuit at the very end. We're not going to form a circuit before that. So that means that A to E is not an option, hence the X that they put through that edge. They also, again, went ahead and erased that for us to show that that's not going to work. So looking for our next cheapest link, looking through all the prices, 150 from B to D would be our next cheapest. Now, notice that B and D actually don't connect to the rest of our circuit right now. A, C, E, we don't have B and D connected. So this is where it is slightly different from what we saw with nearest neighbor and repetitive nearest neighbor, where you start at one point and then go from one to the next to the next. In this, we're just looking for where is the absolute cheapest link that we can find. So we are going to end up using B to D. Notice they've got that marked here for us. The next cheapest, if you're looking ahead, is probably going to be A to D. And in fact, that is the next cheapest. So the next cheapest link is AD, which is 152. So at this point, we are almost done. In fact, we've got everything connected with the exception of ending at E and starting at B, which means all we have left to do is connect those two vertices with that $200 link right there. Even though that is not the cheapest that is remaining, that is the last one that we need in order to close up our circuit. That's what we are showing on this slide. And now we have our cheapest link circuit. So that cheapest link circuit that we just created was A to C, C to E, E to B, B to D, and then D to A. Keeping in mind that we wanted to start and end at A, just like we did on the other problems, so that's why we wrote them in this order. The total cost of this, if you add it up, is $741. Let's go back and look at what the optimal was, which was in 6.3. I believe the cost of our optimal tour was $676. We now have our third and final one that is not brute force, which again was cheapest link algorithm. Let's go ahead and look at its relative error. So when we calculate relative error, we're going to take the cost of that tour, which was $741, minus $676, which again was the optimal tour that we found using brute force, and then divide that by 676, which 741 minus 676 is 65 out of 676, which gives us a relative error of about 9.62%. So what you can see based on relative error, at least for this particular problem, is that our best alternative to brute force would probably have to be this repetitive nearest neighbor, which gave us a relative error of only 6.8%. The second best would have been the cheapest link algorithm at 9.6%, and probably not something we want to use, but nearest neighbor was only off by 14.35%. So looking at those, at least in this particular example, repetitive nearest neighbor gives us the cheapest alternative to brute force method. Obviously, the optimal route we could only find in this case by brute force. That was $676. But you can see that these other methods are a lot quicker than brute force, and some of them get you relatively close. All right. Going back to our cheapest link, let's go ahead and summarize the steps that we took. These next couple of slides would be good ones to copy into your notes for the notes for 6.5 for cheapest link algorithm. Here's what you're going to do step by step. So step number 1, pick the cheapest possible link on the entire graph, which is the one with smallest weight. If it's a tie, then you're just going to pick one at random and mark it. Now, the other thing that if it's a tie, especially at the beginning, is you're probably going to use them back to back because you can have two edges coming out of the same vertex. So the cheapest link at step 1, if there is a tie, you're probably going to end up using both. So it really doesn't matter which one you pick, but just go ahead and pick one at random. Step number 2, pick your next cheapest link and mark it. And then for steps 3 and 4 and so on, you're just going to continue picking those cheapest links, provided that the link that you pick does not close the circuit and does not create 3 edges coming out of a single vertex. So as long as you follow those 2 rules, you just keep picking the cheapest possible link on the graph. And then at the very last step, it calls it step N because you could theoretically go through it a number of times. But at the last step, you connect your last 2 vertices to close your circuit, and that gives you the cheapest link tour. So to take a look at another example, roving the red planet. I think we introduced this in either 6.1 or 6.2. Let's say our job was to find an optimal tour for a rover that was going to land at A, then visit all of the sites along this red planet on Mars, and then end back at A. Here is a graph which shows those distances. I'm going to go ahead and illustrate the cheapest link using this. The rest of the slides talk you through it, but I want to at least work through one example with you guys so you can see kind of how this works. So looking for our cheapest link, and again, I'll use red like they suggested. It doesn't really matter what color you pick. I believe the cheapest link is going to be this 1,300. I'm looking at all of the other ones, and I don't see anything that is quite as cheap. So that's going to be connecting P to W. Our next cheapest link, it looks like, is going to be the 1,500 that connects A to P. Let's see, going through our graph now, we're looking for our next cheapest link after 1,500. I believe the next cheapest is up here, which is 2,000, connecting N to I. All right. Continuing through this, let's see, our next cheapest would be 2,200 down here. However, that would connect W back to A. That would create a circuit, so we are not going to be able to use that 2,200. Our next cheapest after 2,200, let's see. I'm looking around, I think 2,800, which does happen in a couple of different places. In fact, I think, and it really doesn't matter which one we pick, let's go ahead and use this 2,800, which connects I to A, which again is okay because notice that it does not create a circuit. You would still be on an open path WPAIN. It's not as if we are connecting back to any of the vertices we've used before. Now, we also are going to get to use this 2,800, which connects W to H, because once again, that does not create a circuit. It also does not mean that we have more than 3 edges for each of our vertices. At this point, we just need to look for our next cheapest link. After 2,800 would be 2,900. But let's see, that's going to mean 3 vertices coming out of W because we're already using 1,300. We're already using 2,800, so we can't use this 2,900. That would create 3 vertices coming out of W, so that's not going to work. Our next cheapest, let's see, would be 3,000. 3,000 does happen in a couple of different places, but if we were to try to use this 3,000 connecting P to I, that would give both P and I 3 edges that are coming out of it. So we're not going to be able to use this 3,000. However, I think we are going to get to use this 3,000, which connects H to G. Notice that that only gives H 2 edges coming out of it, does not create a circuit. At this point, though, notice that if you go around, all of our vertices have been marked. We've gone to all of them. We now just need to connect our graph. So in order to connect our graph, we just need to connect our 2 circuits our circuit together. That means that we need to look for where we only have a single coming out of it, which I believe means we're going to be connecting G back to A for 7,500. Actually, let's go back. I don't know that G to A is going to work because G to A would then have, let's see, 1, 2, 3 coming out of it. So that's not going to work. Let's see. If we connect G, which only has 1, H has 1, 2, W has 1, 2, P has 1, 2, A has 1, 2 edges coming out of it, N only has 1, I has 1, 2. That means that G and N need to be connected in order to complete this circuit. And now I think we've got everything now with 2, and we've got our cheapest link. So to write out that cheapest link, remember we wanted to start and end at A. So from A, we would go one of 2 directions. Let's just go down to P, so A to P. P to W, from W to H. From H, we would go to G. From G, we would go to N. From N, we would go to I. And then from I, we would go back to A. Let's see if the slides agree with that. So let's see if that's the same as what they come up with for our cheapest link. Now, just as a side note for brute force, if you wanted to find the optimal tour, it would take quite a bit of time. You'd have 720 different tours that you'd be checking. That's going to take some time. So we're going to pass on that idea for right now. Let's just see how good cheapest link does. So they kind of give you a step-by-step there in case you wanted to read through it later. Obviously, I've already worked through it with you and kind of already have an idea of what that's going to look like. So again, their cheapest tour was APW HGNIA, which ours was APW HGNIA. So we did come up with the exact same cheapest link tour that they had. They went ahead and calculated the length of that for us. If you wanted to go back and add those together, you could as well. But it comes out to be 21,400 miles. And then you can see what that looks like on the actual map of the planet for Mars. Now, that cheapest link, again, here, that is shown for us, actually turns out to be pretty cheap in terms of the other methods as well. By comparison, if you were to do nearest neighbor, so remember, cheapest link was 21,400. Nearest neighbor comes out to be a little bit less at 20,100. And then here that is for you, so I won't work through that, but just wanted to mention. Here that is shown on the graph. And actually, nearest neighbor gives us a better tour than cheapest link. And that's going to be the case sometimes. Remember, nearest neighbor was actually the worst besides, in fact, it was the worst out of our four methods for our other example. Now it turns out that cheapest link is going to be worse than nearest neighbor. In fact, come to find out, surprise number 2 is that the nearest neighbor actually turns out to be our optimal tour, which if you were to use a computer or if you just had a lot of time on your hands and did brute force algorithm, you'd actually find out that nearest neighbor is optimal. So it turns out that the 20,100 is the optimal tour as well as the nearest neighbor. So that would be the one you'd also come up with if you're to do brute force. Just for fun, let's go ahead and see what our relative error was. Remember, for cheapest link, we had 21,400 as our value for the distance using cheapest link. Let's go ahead and find that relative error. So we're going to take our value that we found, 21,400, minus our optimal route, which was 20,100, and divide by 20,100. And let's see what that gets us. 21,400 minus 20,100. So we were only off by 1,300. Now that is miles, so that is a little bit to be off. But as a percentage, take that and divide by 20,100. You're going to find a relative error, which is fairly small. In fact, as a percentage, it is 6.47%. So not very far off. Obviously, if you wanted to do that for nearest neighbor, you would get the optimal tour, and your relative error would be 0. All right, guys, I think that's about all I've got for us in this last section. So now you've been able to see all 4 different methods for finding a Hamilton circuit in order to solve a traveling salesman problem. You've seen the brute force, which does give you an optimal tour, but does take quite a bit of time. You've also seen nearest neighbor and repetitive nearest neighbor, which go pretty quick and can get you some pretty good results. And finally, today we saw cheapest link. That being said, we have quiz coming up in just a couple of days. Until next time, guys, have a great rest of your day.